Lab 2, Motion of a Falling Object. Can we successfully model and predict the motion of a falling object with and without the presence of drag? The purpose of this lab was to examine the motion of falling objects in order to understand what contributes to a non-zero net force and what happens to a system in the presence of a non-zero net force. So here's my video and tracker from which I gathered all of my experimental data that I can use to check and build my models. My system is the shuttlecock. Now I had to first establish my axes with the origin at the tip of the shuttlecock and the positive y direction going up towards the top. I calibrated the distance using the door, which was 0.75 meters across. Then I traced the motion of the object, and it is from these points that I was able to get my position and velocity data. The main concept that we wish to explore is why is the system accelerating? It's changing its velocity, and to understand why it's doing that, we need to understand the law of universal gravitation. This law tells us that the force of a gravitational pull between any two objects is equal to some constant times the mass of the first object times the mass of the second object divided by the magnitude of the distance between the two objects. So how fast will something accelerate towards Earth due to the gravitational force? Well, we know that force equals mass times acceleration thanks to the derivative version of Newton's second law. And we know that the force of gravity is equal to this thanks to our law of universal gravitation. So we can make a mass times an acceleration equal to this force right here. And if we substitute the mass of the Earth for m2 and some object for m1, we get this equation right here. And if we divide both sides by the mass of whatever object it is that we have, we'll see that we get the acceleration equals the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. In this case, the mass of the object cancels out, leaving only the mass of the planet and the object's acceleration. This explains why all objects fall towards the Earth or any other planet at the same rate. On Earth, that acceleration is 9.8 meters per second squared. Now this acceleration is unique to the Earth. Other planets will have a different value depending on their mass. However, on Earth, if we take the mass of our object and multiply it by this acceleration, we'll get what we call the weight force. The weight force of the shuttlecock was negative 0.049 newtons. Another major concept that we have to understand is the force of drag. It's caused by friction with fluid surroundings and it opposes motion. So it's in a direction opposite the velocity. It's based on the properties of the object and relates to the velocity. It can be proportional to either the velocity if it's viscous drag or the velocity squared if it's turbulent drag. Now that we understand the concepts, we can begin coding for our model of a falling object. I've got the key assignment statements written out down here. We can see I've got the net force, the weight force, the drag force for viscous and turbulent drag, and a drag constant which I had to specify. Now I picked these values because they gave me the same final position as my observations. So let's see how our models run. First we'll run one without drag, and then we'll run one with drag. As you can see, a little bit of force from drag starts pointing in the upward direction as this one speeds up. So let's analyze and compare our data, and you can see I've got a position versus time graph and a velocity versus time graph. Now the predicted path from the no drag model does not exactly match the observed data. Models with both viscous and turbulent drag come incredibly close to these observed positions. The model without drag starts off close to the observed data, but as the object speeds up, the data sets diverge. This is because the force of drag increases as the velocity increases. This means that the real object must have slowed slightly due to drag, and my low drag model supports this. The net force is in the negative y direction, but there must be a small component of force in the positive y direction. Now, the main source of my data discrepancies here with these graphs is definitely my human error. I had an inexact location of the object's center point. The images in the video were very blurry, and central points were difficult to distinguish as the object sped up. This makes my data less accurate as I attempted to mark the tip of the shuttle, but lost track of it, perhaps moving to the center of the object, causing the distances to be slightly skewed. What does it mean? Well, without drag, the object will continue to accelerate. However, with drag, the force of drag will increase as velocity increases. Terminal velocity is the point at which the magnitude of the drag and weight forces equal one another, leaving the object falling at a constant rate. We can visualize terminal velocity as the slope of the line reaches zero. The high drag model reaches terminal velocity around 2 meters per second. The low drag model, which corresponds to my observations, is just about to reach terminal velocity at about 8 meters per second. But what if the object was thrown downward? Would the terminal velocity in this case be the same or different from the case where the object was dropped from rest? Well, I did it in the model, and we can see my thrown object here has the exact same terminal velocity as the one that dropped. The object is thrown faster than the terminal velocity, but drag slows it down to a very similar 2 meters per second. In conclusion, we were able to successfully gather data and predict the motion of a falling object. The velocity changed, indicating that a net force must be present. The force of gravity was pulling the object down, and we showed this by using the law of universal gravitation. We know that objects accelerate towards Earth at 9.8 meters per second squared, but something slows them down, and that's the drag force. And the drag force opposes motion and depends on the velocity of the object.